Well, let's look at some of the properties of the discrete Fourier transform. Now, there are many properties, and we're not going to look at all of them. You've probably looked at a pretty complete set of properties for the Fourier transform, and most of those also apply to the DFT with the appropriate modifications. Now, here we're going to look at a subset of properties, and one particular property, though, the convolution multiplication property, we're going to save for a separate lecture. So let's begin with the idea of periodicity. And if I have x of n, and I take the endpoint DFT of x of n to obtain x of k, it turns out that x of k is n periodic. That is, it satisfies x of k plus n is equal to x of k. And this is a consequence of the 2 pi periodicity of e to the j omega. Remember, we're taking n samples of the DTFT, e to the j omega, in the interval of 0 to 2 pi. Now the time signal is also, x of n, is also periodic. In other words, x of n plus capital N is equal to x of n. And this occurred because when we sample in frequency, remember we looked at sampling the DTFT in frequency, this introduces aliasing or periodicity in time because we have those replicates of the signal spectrum that show up at multiples of n in the time domain. When you add those things together, you end up with something that has period n. Of course, the DFT is also linear, as with all the other Fourier representations. And in particular, if I have a weighted combination of two time signals, a x of n plus b y of n, that's going to transform to a times the DFT of x of k plus b times the DFT of y of k. Now, the time shift property, as you've seen in the other Fourier representations, there's also a version of that for the DFT. And so, in particular, if I shift the time signal by m samples, then when I take the endpoint DFT, I end up multiplying the DFT coefficients xk by these complex exponentials e to the minus j 2 pi over n k times m. So shift in time multiplied by a complex exponential in frequency. Similarly, the dual of that is the so-called modulation property. And that states that if I take x of n and I multiply it by a complex sinusoid whose frequency is 2 pi over cap n times m, is my frequency, and I take the endpoint DFT of that, what I obtain is a shifted version of the DFT coefficients. In other words, I end up with x of k minus m. Modulation of the time signal shifts the DFT coefficients in proportion to the frequency of the modulation. And then there's the conjugate symmetry property, which we've also seen in the case of the other Fourier representations, and that is expressed as follows. Assuming the signal x of n is real, then I have that the conjugate of xk is identical to x of minus k. And in this case, because x of k is n periodic, this also implies that x conjugate of k is equal to x of n minus k. And these outer relationships here will apply particularly in the case where we're only working with one period of x of k, then it's useful to have this one. Now, as a consequence of this relationship, we can say several things about the real and imaginary parts. First of all, the real part, the DFT coefficients, have to be even. The imaginary parts have to be odd. Similarly, the magnitude of x of k ends up being an even function, and the phase of xk is an odd function. All of these are a consequence of this conjugate symmetry that's associated with real valued signals x of n. Now, the last property that I want to look at in this particular lecture is what I'm calling inversion. And this amounts to proving that the inverse discrete Fourier transform expression, as I've written here, actually recovers the time signal from x of k. So when I substitute x of k, the expression for that, into my inverse discrete Fourier transform, I want to show that I get x of n on the right-hand side of this expression. So we'll make the substitution and write out the result. I have that x of n is 1 over n, the sum k equals 0 to n minus 1 of and I've written in red here the substitution for xk. And you'll also notice that I changed the index of summation to m here because we already had an n up in this expression for the inverse, and so I can't use n for an index of summation. Okay, I need something else. So we're going to have the sum m equals 0 to n minus 1 of x of m, e to the minus j, 2 pi over n, k times m. And then all of that is multiplied by e to the j, 2 pi over cap n times k times lowercase n. Now if we interchange the order of summation and group some terms, I can express this as I've shown here, where I've pulled out x of m and the sum on m, and then I've collapsed the exponents using the fact that they're both powers of 2 pi over n to the kth. We've got both here, we've got a k, and in here we've got a k. So I can pull that outside and write n minus m on the inside. What we're going to do is simplify this expression now, because we can evaluate that in closed form, it turns out. In particular, what this term represents, a sum of complex sinusoids. I can regard k as my index because that's what I'm summing over. I can regard that as my sort of, quote, time index here in thinking about this sum. And n minus m is the frequency of these sinusoids. Now what's unique about this is that the frequency is always a multiple of 2 pi over n. In other words, capital N is always a period of this, no matter what case I consider. For any value of n minus m, I always have a period, capital N. So I'm adding up complex sinusoids over one period. Consequently, they add to 0 whenever n is not equal to m, and then they add to 1 in the case where n is equal to m, because that's a complex sinusoid of frequency 0. If I use this fact for this sum, that it's only equal to 1 when n is equal to m, that implies then in this x of m here, I'm going to replace m by n and drop the summation, because the only time I get a value is when m is equal to n, and lo and behold, we have the desired result. On the right-hand side, we've shown that x of n is equal to x of n, and that therefore the inverse DFT expression does indeed invert the DFT.